Hi everyone and welcome to a new video. In this video I would like to discuss the magnitude and the frequency scaling in filter design. I have previously discussed the LC ladder filter configurations and also the design step for several responses like the Bode and Chippechow. There we use the scaling, and there were some questions about how do we do scaling for capacitors, resistors and inductors. So this specific video is to illustrate that for really simple circuits and also how you can calculate now the scaled up version of your components. Of course, we'll work out some examples and work out the calculation step by step and also verify these in SPICE simulations. So let's look at our first, the scaling. The scaling can be done using the magnitude scaling or impedance scaling. The process is actually increasing all the impedances in a network by a factor. Let's say we increase everything by a factor of 1000. So every impedance is increased by that factor. The frequency response remains unchanged compared to the original circuit. So that is here the case, only for magnitude scaling. We will see that shortly and what it means. And for magnitude scaling, we will use the factor K sub m. And that is just a value for your scaling. Now for our resistor, we denote the R prime as the scaled up version is equal to the Km times the unscaled value of your resistor. For example, if you scale up your resistor from 10 ohms to, let's say, 1000, then your Km will be 100. And that is actually the magnitude scaling factor for this case. For the inductor, it is like this. So you have your unscaled and a scaled inductor values, again with a prime. And for the capacitor you have this value, which is then C over Km. So the unscaled over the magnitude scaling factor is the scaled version for your capacitor. The frequency is, as said before in this second bullet, it's exact same as before, so that doesn't change. So the scaled frequency is again equal to the unscaled frequency. Now that is just considering the magnitude scaling only. Now when you now do only the frequency scaling, what happens? Now that is a process of shifting the frequency response over network up or down. So you actually make a shift in the frequency only, and impedances remain also unchanged here. So that is actually the reverse case of the magnitude scaling. So for that frequency scaling we use the coefficient or the parameter Kf, so it's denoted by this letter. And now we have the following formulas. The R, which is not dependent on the frequency, so the R prime, which is the scaled version of the resistor, is equal to the unscaled version of the resistor, so that is exact same. The inductor will be like this, so the unscaled inductor value divided by this frequency scaling factor will be your scaled inductor value. And the capacitor is the same. And now for the frequency, because that does change, because that is where we go up or down, this value will be then multiplied by the unscaled frequency. It can be a cutoff frequency, it can be a center frequency in your design, and that will be then your new frequency. Okay, again denoted by this prime. But we will like to also do this together, so magnitude and the scaling for the frequency together, so that can be done using this. So you can say, I do the magnitude and the frequency scaling, so what are the formulas? Now these are the formulas together, where we have discussed this here. So you get now the R prime, L prime, C prime, also the omega prime. Now you see also the combination of these two, and these two, and these two here, everything at once. Okay, let's now use these equations and see what we can do in the specific examples. First example is about the RC low pass filter, which is a very simple filter here, which is an R and a C. You see here the prototype filter, which has normalized values, 1 ohm and a 1/3, not really practical, but we already start with these values. I would like to have the following. We like to use the scaling to shift the cutoff frequency of this filter to 4 kilohertz. And we would like to use a resistor of 1 kilo ohm in the final design. So as said, this is the prototype circuit, or it's also called a normalized circuit. And we will use this to go up to our specifications. Okay, Now, the solutions, first the calculations. We look at our prototype circuit first, and we see the R is 1 ohm and the C is 1 farad. Now, we also see that the cutoff frequency in radians per second can be calculated like 1 over RC for this very simple passive circuit. That is 1 over 1 times 1, everything is just 1, actually it is 1 radians per second. Or in the hertz is omega C, which is the cutoff frequency in radians per second, over 2 pi will be then 0.159 hertz. That will be now scaled up to this 4 kilohertz. So that is also what we need to do. Now, going to the scaled circuit, as said before, we need to make now the frequency scaling, and that means frequency scaling factor Kf. Now, since we deal now with the shifting of the cutoff frequency, that means the omega C prime over the omega C originally, which is 1, that will be our Kf. Now that means then 2 pi times 4000, that's of course the omega is equal to 2 pi f, over 1, which is what we had originally from our prototype circuit. That will be then this, and it will be then 8000 pi. So that is now our frequency scaling factor for calculating the values for the final design, because now the R prime in this case must be 1000 or 1 kilo ohm, so this is actually the value here. Then the scaling factor will be actually just R prime over R, which is just simply 1000 over 1, because we have the 1 as our original value, which is just 1000. So we have now the frequency scaling factor and also the magnitude scaling factor. Then the scaled component values are as follows. So the R, as said before, which is just straightforward calculation again, 1000 times 1 will be 1000 ohms, or as said before, so that's required. Now the C prime, which is then C over Km times Kf. This is the formula we have discussed previously in general form. Now we have the C is 1, Km is 1000, and the Kf is 8000 pi. Now when you now calculate this, you get now 39.79 nanofarads. Okay, this is now the final design. We need a circuit. That means we need to shift this or scale up to the design circuit here, which has a resistor R prime, which is 1 kilo ohm, and a capacitor, which is 39.79 nanofarads. And these are all primed values. Okay, this is then the scaled circuit. Let's see if this is really doing the job. So we need to look at it in the simulation results. This is the Bode plot. You see here the pink magnitude plot. That's for the prototype circuit, normalized. The blue one is for the scaled version. You see the cutoff frequency we have determined, also calculated, which is 0.159 hertz or 159 millihertz. That's as shown here. It's also label A here, which you can see that here, because the baseline is a 0 dB. You go down by approximately 3 dB and you get actually your values. And when you now shift this, you see this blue line, and there the cutoff frequency is indeed 4 kilohertz as required. You can also see that in the label B here. The circuit here in the SPI simulator is also shown here. So you see the 1 ohm and 1 farad for our prototype circuit, and also the 1 kilo ohms and 39.79 nanofarads. So that means this circuit is indeed, according to specifications, scaled up to 4 kilohertz as a cutoff frequency. So it means it is according to specifications. Okay, let's now look at another example where we see the RLC bandpass filter, which is this given here, which has a series resonance circuit, L and C, and there's a resistor R here, which is then at the output, and that behaves as the load. We like to shift the center frequency, which is also called the resonance frequency, to 5 kilohertz, while keeping the quality factor the same. So the quality factor we have here, which will be then given shortly the values for our prototype circuit, must be the same as our shifted version. And we need to use an inductor of 20 millihenries. So again, this is the prototype circuit. And when you now look at the solutions for the calculations, the prototype circuit has everything 1 ohm, 1 farad, and 1 Henry. So everything is here 1, 1, 1. Now when you now look at the center frequency, the calculation for the center frequency is 1 over the square root of the product of the inductor and the capacitor values. They are again 1 and 1. That means we have here 1 radians per second as our center frequency. But going to the bandwidth, that is this formula, which is R over L, which is 1 over 1 again, because everything is 1. That means 1 radians per second. Now, what is the quality factor? The quality factor is the center frequency divided by the bandwidth. It doesn't matter if you get now here radians per second, or hertz. You get actually a ratio here, which is 1. That means our final circuit must have also a quality factor 1. So our Q prime must be also 1. Okay, this is now our reference. We now go to the scaled circuit. Now for the scaled circuit, we need to first determine now the frequency scaling, because that is what's happening here. The frequency scaling factor Kf is now related to that shift in the center frequency. The center frequency goes up from 1 radians per second to 2 pi times 5000. That's actually this ratio. That means 2 pi times 5000 over 1, which is then 10 to the power 4 times pi. This much. Okay. This is the frequency scaling factor. Now, since the L prime must be 20 millihenries, that's already given in the example, we have now from this formula we have discussed earlier that the L prime is equal to Km over Kf times the unscaled or normalized value of L. Now, we now substitute the values. We know that L prime must be 0.02 or 20 millihenries. Km we need to determine, but the Kf is already determined here, and L itself normalized is 1. Now we can now calculate this Km, which is just straightforward, which is 0.02 times 10 to the power 4 pi. We get now here 628.3 approximately. Okay, now we have everything. We have our scaling for the frequency and also the scaling for our magnitude. So these two factors are now available. We can now say, let's now calculate the other scaled component values as shown here, because the R prime, which is then the scaled up version of the resistor, will be then the Km times the normalized value, which is 1 here. That means 628.3 times 1, which is then 628.3 ohms. That's straightforward. The C prime, which will then C over the Km times Kf. Now we have now these two, and also the C, which was 1 originally. So 1 over the Km and the Kf. That will give us 50.66 nanofarads. So we have now our L prime, which is already given in the example, and also the R prime and also the C prime. So that means the complete component values are available now. So this circuit prototype will be then transformed in this circuit with all primes here. That is our scaled circuit. Let's also check the quality factor Q, which is then Q prime in our scaled up version. Now the omega bandwidth, so the bandwidth will be then R prime over L prime, which is then this value using the new resistor and the inductors. And we have now the Q, which is then the center frequency scaled up, and the bandwidth scaled up. We calculate this, which will be then 1, approximately 1. By the way, this is actually, if you do the calculations exact, it will be then also 10 to the power 4 pi. So that is actually what we have here. So that means it is as required. So the quality factor is the same as before. So Q is equal to Q prime. Okay, going now to the simulation results for this circuit and also the values here. What we have is now this Bode plot. You see the pink, which is for the normalized or our prototype circuit, and the blue one, which is for our scaled up circuit. And this is the circuit for both of them. So you see the L, C and R, and now the L prime, C prime, and also the R prime, and also the values here for our final design. Now, you see here the center frequency here for the prototype circuit is 159 millihertz as we have calculated. That's also shown here in the label A. In the label B here, we see that the center frequency is 5 kHz, also shown here, so 5K. That is as required, so that means it is according to specifications. Alright guys, we have now discussed two different examples where we use the magnitude and the frequency scaling factor, first with the low pass filter and then this time with a band pass filter. If you have any questions, comments about these examples, please let me know and I will try to answer them as soon as possible. See you next time in another video. Take care.